the fundamental theorem of calculus, which has two parts. The first one is the differentiation of an integral defined function, and you can read that right here. I'm not going to read it to you. The second part is the evaluation of a definite integral, where you find the antiderivative and then plug in a and b, and you subtract the lower limit from the upper limit. And that one is for area under a curve, accumulation applications. But when I think of a free response question as a fundamental theorem question, I'm typically thinking of this upper one, where you are doing the derivative of the integral defined function. And the trick is you take the upper limit and you plug it in for t. And so from some constant to a variable, you plug that in for t and you get f of h of x, and you have to remember that you always multiply by the derivative of what you substituted. And sometimes you can have a lower limit that is a variable as well. And if that is the case, then you would continue this by doing minus, and I could finish this by saying f of a times the derivative of a. And so if that lower limit is a constant, then that derivative of a would be a 0, and it would wipe out that second term, which is why I didn't have it here originally. But if it's a variable, then you would have to plug that in as well and multiply by the derivative of what you plugged in. But that is when you are finding the derivative of the function that is represented by that integral. So let's look at a free response question. This one's from an old AP exam. I don't know what year this is from. You could probably type in that first line in Google and figure it out. But notice we have the function f consists of 3 line segments, and that is what is provided. We have a line here, here, and here. And then they define g of x to be the antiderivative from 1 to x of f, and that is an integral defined function. And when I see one of those, usually, this is not always the case, especially in multiple choice where there's not much to it, not many questions. But in a free response question, if I see an integral defined function, I will almost always start by finding the derivative of g, and that would be by plugging in x for the t. So that'll be f of x. And technically, you should multiply by the derivative of what you substituted. In this case, that's just a 1. So it turns out that g prime is equal to f. So when they said they gave you the graph of f, they are also giving you the graph of g prime, because f and g prime are the same. So now let's look into some of these problems. Let's compute g of 4 and g of negative 2. Notice they did not say g prime, so this little thought that I had right here, not really going to come into play yet. G of 4. Let's see. My g's are weird. That's a little better. So g of 4, first step is just going to be algebra. G is the function from 1 to x, so g of 4 would be the, not the function, the antiderivative. The antiderivative from 1 to 4 of f of t. So my first step is just an algebra maneuver. Replace the x with whatever number is in its place. And then we have to use our calculus knowledge. That is an area question. So the area from 1 to 4, I'm looking at this. So there's 1. And what I'm seeing that's going to help me out is the positive area from 2 to 3. That triangle with an area of 1/2. I have another triangle with an area of negative 1/2. Those two will cancel out. So really all I need to do is find the area from 1 to 2. And so I see a square with the area of 1, and then I'm going to add to that the triangle. And that triangle has a height of 3 and a base of 1. So half of 3 times 1. And when you work all that out, you end up getting a value of 5/2. And then g of negative 2. Antiderivative from 1 to negative 2. Another question, another area question. And fortunately, the area from 1 to negative 2 is just a single triangle with a base of 3 and a height of 4. However, You need to remember that if you are traveling from right to left, that is a negative direction. We're going from 1 to -2. So the area of that triangle is 6. However, that right to left direction means that that is a negative area. So we have an area of -6. So there's your answers to part A. Part B, the instantaneous rate of g, which is a very, very fancy way of simply saying g prime. With respect to x, actually, I could continue that underlining all the way around. So the instantaneous rate of change with respect to x, that is a fancy way of saying g prime of x at x equals 1, just means find g prime of 1. My g's are really hurting. G prime of 1. Well, g prime of 1 for me is going to be really easy because when I first read the problem, I made the connection between g prime and f. So g prime of 1 would equal f of 1, and f is the function that is provided, and f of 1 is equal to 4. So there's your answer. Not much to that one. Really easy to do if you make that connection. So that's more work in your brain than there is in your pencil. Very quick answer. Let's see. Moving on to C, find the absolute minimum value of g from -2 to 4. And this one, this is a fundamental theorem question. However, they have thrown an extreme value theorem question in here. And so this is the extreme value theorem. And anytime you're looking for an absolute max or min on a closed interval, you have to consider your candidates. So my candidates are my endpoints, which are x equals -2 and 4, and your critical numbers, which are when the derivative, this is of g, not f. I need to erase that. That shouldn't be an f. This should be when g prime of x is equal to 0. But we know that g prime is the same thing as f. That was that note we made note of at the very beginning of the problem. So when does f of x equal 0? Well, remember, this graph is f of x. And if this is f of x equals 0 at, looks like -2. And again at 3, -2 was already a candidate. So 3 is the one that I'm interested in. And we are looking for the absolute minimum. Okay. Here's one where this problem is going to be kind of nice. I'm going to eliminate 3 because at 3, f, which is g prime, remember we said a long time ago that g prime is the same thing as f. Well, f changes from positive to negative, above the x-axis to below the x-axis. That means that x equals 3 is a local maximum. And if you're looking for the absolute minimum, a local maximum obviously cannot be the right answer. So I'm going to make a note that x equals 3 is a local max because g prime, which is f, changes from positive to negative. So I am eliminating 3, and now it's down to only -2 and 4. And here's what I referenced a minute ago. This one's going to be really nice because in part A, we found the values of g of -2 and g of 4. G of -2 was -6. G of 4 was 5/2. And so I'm allowed to just import those answers. G of -2 was -6. G of 4 is 5/2. I'm looking for the absolute minimum. Therefore, and it does say the minimum value, which means the y-coordinate. The minimum value is -6. And there is your answer. It does say justify your answer. In an extreme value theorem case, your justification is all of this work. It's showing that you've considered your endpoints. You've considered the critical numbers. Anything you eliminated, you have explained why we eliminated them. We had the values of the endpoints. And so this work is sufficient justification for your answer. Then that brings us to part D, the final part. The second derivative of G is not defined at 1 or 2. Now remember that this graph of F is also the graph of G prime, and you see corners there, so the derivative of this graph would not exist. Those are non-differentiable points. How many of these x coordinates? Now that's an interesting question. Not which one, but just how many of these x coordinates are points of inflections, and justify your answer. Okay, so there are two ways to justify an inflection point. My first thought is that we need, if we're talking about the inflection points of G, we need G double prime to change signs. However, there is an easier way for this problem, or we have the derivative of G, we have G prime, and a function has an inflection point when its derivative has local extrema. If the derivative has a local max or min, that is an inflection point. And I'm going to go with that second route because I can simply look at this graph and I can see that G prime has a local max at x equals 1 only. Therefore, and this is where the question's weird, how many of these x coordinates are inflection points? There is one inflection point. If you look at x equals 2, that is a non-differentiable point. However, that is not a local max or a min for the graph that we are looking at, G prime. So that would not be an inflection point.